Hello, everyone. Welcome to the class of IME 465. Today is March the 30th, and we're gonna first finish lecture 7 LDA and then start the support vector machine, which is lecture 8. First, let me stop my video and share my screen. Okay, let me first finish lecture 7. Here we go. Okay, so let's have a very brief review about the feature dimension reduction section about LDA. So as we mentioned, we can, in the eigenvalue decomposition part, we can actually make it to this form, right? This form. So the good point of this form is that by doing this, our covariance matrix here is actually I, the identity matrix. So applying this idea, we can change the coordinate system of the problem. So here we transform x star to be d to the inverse square root times vt and x. This is exactly as here. See it? The difference that here I don't have the mu, which is the centroid or a shift. Exactly this part. And I've proved here that by doing this, I can actually predict the target by this way. And this is equivalent to our previous decision rule here, decision rule 4. It's equivalent, okay? And indeed, after doing this, we will not have any rotation. And the covariance matrix after the transformation will be I, the identity matrix. And the result is right here, okay? So the idea of feature reduction is that from this idea, from this picture, this result, we can see that we can actually do what? Do a feature reduction. That this is a 2D, and I can make it to be, I can observe in this direction. If we observe in this direction, then we can transform all the parts, all the data part X here to the new covariant system, and hence reduce it from 2D to 1D. And in general, the case is that suppose we have m directions. Sorry, suppose we have m classes, and we know that to get from these m classes, we actually can get what? We can get subspace, spanning subspace by n by this k centroids, by this m centroids, which gets a rank of at most m-1 or m-1 dimensions. For example, m equals to 2, then from 2 points, 2 centroid, you can draw a line. If m equals to 3, then we can get a plane, through 3 points, similar. And then we introduce the Fisher's linear discriminant. Fisher's linear discriminant, the idea is that we want to maximize the between class variance relative to the within class variance. And the mathematical form is in this way, this one. And then we use some tricks, basically nothing but what? But Lagrange dual. And then we can show that any optimal solution must be what? Must be an eigenvalue of sigma inverse B, this matrix. And then not A, okay, sigma inverse B. And then the question is, which eigenvalue should we find? So after the transformation here, we know that the objective function here, is actually equal to eigenvalues. Then, of course, if we want to maximize it, we're going to choose the what? We're going to choose the maximum eigenvalue. In other words, the A should be the eigenvector corresponding to the maximum eigenvalue. And similar, if we want to minimize it, we're going to choose the smallest eigenvalue, okay? Or let's say A should be the solution, should be the eigenvector corresponding to the smallest eigenvalue. So using this way, we can first get the maximum eigenvalue lambda 1, and then what we're going to do is that because remember we need to find n-1 such directions rather than just one direction. So A1 of course is the maximum eigenvector, is the eigenvector corresponding to the maximum eigenvalue. This is going to be the first direction. After getting the first direction, how to get the second direction? Usually, for a spanning subspace, we want to what? We want to find these coordinates such that they're orthogonal to each other, right? Now, what we can do is that we can take advantage directly from the eigenvalue decomposition. Don't forget that in the eigenvalue decomposition, all eigenvectors are what? Are orthogonal, right? This is a fact. And we don't need to worry, for example, whether the eigenvalue decomposition exists or not. It must exist. Why? Because sigma is what? A positive definite matrix. That's why we must have it, okay? And then we can just simply let AL equals VL for L equal to all other directions. G is the number of dimensions that you want to have. G is at most n-1, as we mentioned. G could be smaller than n-1. And then we simply take, the corresponding, the second biggest one as the second direction, the third biggest one as the third direction, and so on. So in this way, we can successfully get all of these AI, A1 to AGs, okay? Now the question is, I give you a point. Let's say X. What would you do? First, I'm gonna transform all the training data from the original data space to what? To my new coordinate data space. So in this way, the first we call it the discriminant variable. Actually, let me get bigger. Oh, in this way? Okay, good. So the first coordinate will be what? Will be xi project onto A1, right? So this is going to be the coordinate of x1 on the A1 direction. Let me draw a figure. I think that's going to be easier to understand. Let me open the word here. So consider this. It's not easy. Let me do it easy way. Let me open the Excel. That's the easiest way to directly draw things. Okay, now suppose I have a direction in this way. Suppose this is vector. Let's say this is, let's say, vector x. Okay. Now my coordinate system, for example, is in this way. Let me make it bigger. Change a beautiful color. 1.5. Let's say 2. Okay. So this is my coordinate system. For example, this one is called. For example, this one is called A1. A1. And the second one is called A2, for example. And A2 would be something like this. A2 should be orthogonal or perpendicular to A1, okay? Now let me ask you, what is the corresponding coordinate of x on A1 and A2? Let me make it, a bit like this way, rather than 45 degrees. Simple. How you would do is this. You're gonna get this distance, right? From here, oops. You're gonna get this distance from here to here, right? And then the corresponding what? The corresponding coordinate equals to this. Equals to equals to this. Very simple, but it's not simple to draw. Right? This is the what? The coordinate in the new system of x in A1, right? But the question is, how would you calculate this length? Isn't it the what? Isn't it the projection, right? the projection of what? X and A1, right? You're gonna have X, A1. So very similar. If I have, you know, the X to the A2, the same. Oops, it should be this. The same. It's gonna be what? Projection of X onto A2, A3, A4, AG. Exactly the same. See it? That's the reason why I claim here. That's the reason why I claim here that each one you just need to project it. That is for AI, okay, the training data, and then do it for all the training data, and then you're gonna do it for what? You're gonna do it for the target data, because I'm asking you to what? To label the training data. Sorry, this is the target data. Here's a typo, and the target data xt, because I'm asking you the label to predict the label for target data xt, right? So you're gonna do the same for target data. Now everything's already what? On our new system, you know, with the discriminant coordinates A1 to AG, okay? Where G is less than or equals to M minus 1 usually is less than D, okay? Now let's, yes.
So here A1 and A2 are unit vector, right?
Sorry, A1, A2 are what?
Unit vector, like their value is 1.
No, they don't have to be. And it's not a big deal. If you want to make it a unit, yes, you can make it a unit. It's not a big deal. You know what I mean? Why? By the way, why? Your A would have many, many different solutions.
Yeah, but
however, I think you're correct. Yes, you're correct. What I'm telling you is usually, theoretically, A can have infinitively many. Let's say A1 can have infinitively many solutions. Why? Because of this. Have a look at this form. Let's have a look at this form. See it? Suppose A1 is a solution, then any k, scalar k times A1 is also a solution, right? Which is nothing but to rescale the norm of A1, make it longer, smaller, right? However, as we mentioned, this is through what? Eigenvalue decompositions. In most cases, people define, you know, eigenvalue decompositions, the eigenvectors are normalized. So in other words, in most cases, I believe for almost all this kind of apps, for example, MATLAB, you know, or this kind of mathematical package, it's gonna give you an orthogonal matrix. In other words, the eigenvector is gonna be orthonormal. And then I think you are correct. On default, we can always assume that all A's are unit. Yes.
Okay.
Yeah. Okay. So that we will have what? We will have all the data converted to the new system. The next step we want to do is that we want to calculate the centroid under the new system again. So the centroid is going to be in this. The centroid I'm talking about what? Of the training data, okay, of each class. And again, this delta is the indicating indicating function. Here, delta yi equals to k, meaning that it's for the class, okay? Here, nk is the number of total classes of data in class k. After doing this, we're going to do the same here. Remember this rule, this decision rule is provided by here. Oops, I got an email. Anyway, it's provided by here. See it? But the difference that here we're still in the original coordinate space, while here in 26 we're already in the new space. See it? And it's proved before already they're equivalent. So in this case, clear, we're gonna do the LDA classification easier. Why easier? Because of data, the dimension reduction. Clear? Okay. Yesterday I made a very cute example, and I'm happy about it. And let me show it to you. To save the time, I directly show you the code. I'm not gonna code it again. And here we go. And I'm gonna directly give you the result. And I'm gonna ask you to see something interesting. Said, are you there?
Yep.
Okay. Have a look at the screen. Let me ask you this, guys. That's very fun. Can you tell me how to do classification? Okay, red points, and all of you can see, right? Red points and blue points, they indicate the two classes, okay? Can any one of you tell me how to do the classification? Arap, you are the formal student here. How to do the classification? Can you tell me? Or can anyone
So
teach me how to do the classification? I don't know.
do you have my sound?
Yes, yes.
I think we can project it in a higher dimension. I mean,
Said, you are really smart. However, you know what? I'm actually confusing you by doing the reverse way. This is from a higher dimension. I showed you this angle just to tell you how terrible if you choose a bad direction. And the truth is that this is a 3D, and I have this. Wait. See it? Now you understand? Get a point? Everybody get a point? Okay, it is 3D. The thing is that just now, this is a z-axis, x and y. X and y doesn't matter. Z is important, okay? The thing is, just now I showed you this angle on purpose. And you can see, from this angle, what the hell, who can do the classification? They're the same, right? However, if we use Fisher's discriminant, we can actually go from this way. See it? And this way is very, very clear. You get my point? Because of what? Because from this direction, see it? The relative difference is gonna be somewhat the biggest. Okay? Again, recall Fisher's discriminant formula here. This one. This where? This one. This picture. See it? The between class variance, you know, relatively the maximum between class variance relative to the within class variance. Okay. So if we have a look at this angle, not necessarily this angle, you know, maybe a little bit different, but for sure not like this way. It should be somewhat like this way. Then it's very easy for me to classify. Get a point? And then from this angle, everybody knows how to get a point, how to classify, right? What you need to do is to find this coordinate system that's gonna transfer your data from this terrible view to this beautiful view. Get a point? Okay, that is the power of the rotation, the coordinate rotation, and meanwhile reduce the dimensions. Why? Because from here, first of all, this data, the truth is that it has 3 dimensions, okay, 3D. And if we make it in this way, guys, actually we need how many dimensions? We need only 1 dimension. You see what I mean? For example, I create a line, something like this way. For example, okay, it's not accurate. I make a line this way. Then isn't it very simple? You just need to project the number. If who cares where the number is? Because a centroid must be somewhere like this way. Centroid must be somewhere like this. Okay, one centroid maybe here, one centroid somewhat maybe here, you know. And then I just need to compare these 2 centroid, and I'm done. See it? So that I can create the data, I can reduce the dimension feature space from 3D to 1D, and meanwhile, it's going to be extremely clear. Everybody knows how to do classification from this figure, right? Clear? That is the motivation, okay? And in discussing PCA, we're going to discuss more about it. Again, remember, this eigenvalue decomposition is just a special case of what? Of singular value decomposition, where the left and the right singular vectors, left and the right singular matrix same, okay? Because here you have U sigma inverse, U sigma UT. While in the singular value decomposition, you're going to have U sigma VT, okay? Very good. Any questions here? No? Okay, let's continue. Let's go back to our lecture notes here. Okay, so finally, this is an example. This example is again copied and pasted from the Element of Statistical Learning, which is really, really a good book. And here we have a data of vowel recognition. So this is nothing but kind of like voice recognition. For example, you read the different words, and it's gonna you know, listen to many people read different words, so that it's gonna automatically recognize people's, you know, speaking, or people's, you know, this kind of vocabulary reading. Now we have 10 dimensions. However, in this class, somewhat special is that we have 11 classes. This indeed, the number of classes is more than the number of feature. But it doesn't matter. Later you're gonna see we only need 2 dimensions. We don't need 10 or 11 dimensions at all. We just need 2 dimensions. And these 2 figures, this shows you, because it's a 10 dimension, you know, you cannot draw a 10D, right? What we do is that we compare. What we do is that we compare different coordinates. For example, this is coordinate 1 and this is coordinate 2. Here, coordinate, what I mean, are kind of like original coordinate. And then this is a training data, which depends on only 2 coordinates. However, be careful. Here, they're canonical coordinates. Canonical coordinates is the same as the A1, A2 here, okay? It's discriminant coordinates already. It's also called canonical coordinates. So this is a classification result. By contrast, if we want to run more coordinates, for example, we're going to see coordinate 1 versus coordinate 3, 2 versus 3, and then 1 versus 7, and the worst case is 9 versus 10. Especially in 9 versus 10, what can you see? All of them are together. See it? This is exactly what? This is exactly this case. Here's 9 versus 10, the result. See it? Which is really, really bad. So this shows you that actually we don't need really 10 dimensions. We only need, for example, 2 dimensions. The question is you need to find a very smart way, a very good way that you can nicely see the dimensions. Okay, the difference, what I mean. At one direction that it's different classes will differ the most. Something like this way, rather than something like, for example, this way or this way, especially this way. Everything, they are just together. Who knows which one is which? This one is also very close. See it? Okay, that's everything about LDA. Any questions? The most important thing, the most important here is what? The idea about this coordinate rotation, okay? And the idea of the reduction. The idea, the LDA model itself, I think it's rather simple. Why? Because it's very, very similar to what? To the logistic regression. Remember it? Both of them also have this, but the difference is that in traditional LDA, we assume what? We assume that the data, given the classes, the data distribution, I should say the conditional data distribution is what? Is Gaussian, okay? And all the classes share the same variance. This is the assumption of traditional LDA. While in the generalized LDA, we dropped this condition. And it's more clear to see that it is indeed a linear classifier because of this. It's linear, okay? Good. Let's go to lecture 8, SVM then. I would say that personally, SVM means support vector machine. I would say that personally, SVM is my favorite classifier. And it's very simple, and it usually results in very, very good prediction accuracy. And here I also included a section about the kernel technique or kernel trick, in which you can see actually the decision boundaries can be something curved rather than just, you know, a hyperplane. Okay, let's formally start with the story. So let's consider a two-class classification problem. So still using the same notation, okay? We label the y as -1 for class 1 and a +1 for class 2. Now the thing is that we consider hyperplane as the decision boundary. This hyperplane is called the separating hyperplane in this way. Is this form familiar? The same
exactly.
as what?
We have the LDA in LDA.
Sorry? Yes, in the LDA.
Yep.
Yes, it is the same as the general LDA form. See it? The difference is that it's called a YX. Here I use FX. The reason I don't use Y is to distinguish this decision function versus the data YI. Otherwise, it could be some, it could have caused some notation confusion. Then the thing is that for a data I, if I have fx less than 0, then which is corresponding to the y equal to -1. Then we predict it to class 1. And if it is fx greater than 0, then we predict it to class 2. The question is, what if I have exactly fx equal to 0? So in this case, it's gonna be on the decision boundary. Okay, it is gonna be something like this way. And this figure is actually copy and paste from lecture 7, the LDA case. Now the thing is, we want to calculate. Suppose the decision boundary line is given. This separating hyperplane, it is WT x plus W0 equals to 0. Okay, for a given data x, I want to know the distance from the data to this separating hyperplane. How to do it? Remember this figure in lecture 7? I just closed it. Let me open it. Where's my lecture 7? Lecture 7, come on. Okay, here we go. Lecture 7 here. So in the lecture 7, it is here. This figure, remember it? You have two methods. First method, as I introduced here, you can take advantage of this, triangular function. Let's say this one equal to sine of theta, and then you get this a, you got sine theta, you have this, and similar, this x equal to this plus this, right? And by multiplying multiplying a WT and then plus a W0, you immediately get this. Okay, the difference that here the R is something like a vector, but in our lecture 8, I directly define Ri as the distance, so that I added an absolute value here. Okay, so simple. My Ri equals to absolute value of fxi over the norm of W, which is this. Clear? Okay. And you may ask, hey, what if y is negative? Sure. Y is negative means what? Means fxi is negative. So negative times negative is positive. So this is indeed the distance. Of course, if you really worry, you can still add a absolute value. No difference, actually. Okay. The reason I'm writing this way is because from here, we can define the so-called hinge loss. Have you heard what is hinge loss in statistics courses? No? Okay. Hinge loss is mostly, first of all, hinge loss is a loss function. It's something, the same as, for example, we have introduced, for example, square loss, absolute loss, 0, 1 loss, this kind of loss functions. Hinge loss is mainly used for this kind of maximum, minimum margin classifications. And we're gonna see the idea after it. Give me several minutes. You're gonna see why it's so important. Okay, to continue our story, for a classification problem, what we want to do is kind of like to distinguish two classes, right? Here in this lecture, except for the last section, section 4, in all other sections, I assume I have only 2 classes, okay? I don't have more than 2 classes. So I want to distinguish the 2 classes, right? It's something similar like this example here. I want to distinguish these 2 classes, and I want to find a direction in which the 2 classes are different at the most level, right? I'm not going to do like this way because really no difference at all, right? Okay, so to achieve this point, we actually want to find a separated hyperplane such that the difference between the 2 classes along the normal direction, of course, of this hyperplane separate plane is maximized. What does it mean? So for example, consider the data here. So class 1, class 2. Now, this is class 1, this is class 2, it doesn't matter. Now, I want to see what is the difference between, class 1 and this separating hyperplane. So when I say a distance between a set and a line, that means what? That means the minimum. The minimum point, the point in this set which has the minimum distance to the line. For example, here in this case, the distance from the hyperplane separate plane to class 2 is this, and that from the separating hyperplane to class 1 is this. Okay, and I want to find a line which is gonna maximize this distance. For example, I have many choices if I don't want it to be maximized. For example, I can, oh no, let me delete it. I don't want to use that. Let me use this color. For example, I can choose in this way. But choosing this way, see it? The distance is actually similar. Actually similar. Well, anyway, let me, this is really a very bad example. Let me draw another example to make it very clear. No, something, let's try something like this way, okay? So suppose I decide to make my separating hyperplane in this way. Then what you will have, I don't have a dashed line. I don't have a dashed line. Anyway, let me use this one. Then the minimum distance is here, see it? And the minimum distance is here. And clearly what? These two distances is what? Smaller than this distance. See it? So that our red one is better. You know what I mean? You can just rotate, you know, this red line. You have many different, you have many different choices, you know. And you want to find the line such that the distance is gonna be maximized. Okay, so this is the idea of optimal hyperplane. Okay, and which is also the basis, the key of the support vector machine, SVM. Okay, so how to formulate it along this original idea? What we're gonna do is this. First of all, we want to find the minimum distance between this and this, right? A very easy observation is that this line, the separating hyperplane, is always going to be in the middle. By in the middle, what I mean is that the distance from this line to class 1 should be equal to the distance from this line to class 2. This is class 1. From this line to class 2 is equal to the distance from this line to class 1. You know why? Because simple. As long as we've determined, you know, this is too much. Let me try to make something like this. Okay. As long as I have the slope, I've determined the slope of this line, I can just parallelly move it. You know what I mean? I can always move to a point to the line such that these two distances are the same. And there's no difference. Why? Because I want to have kind of like, you know, the summation of two. Or, you know, because you definitely cannot have the minimum of them, okay? Otherwise, I'm going to draw a line this way. I'm so bad in drawing. For example, I can draw, I'm going to draw a line like this way, just to pass the point. Then the difference is 0. Of course, this is very ill modeled, very bad. I'm not going to do it. So that I'm going to always move it to the middle, so that I don't need to care for the two parts. I only need to care one part, right? Okay. The second thing is that again, by the definition, what is the minimum distance from class 1 to the hyperplane? The minimum distance means this. For all points in one class, what is the minimum distance to the line? And as we've mentioned, the distance to the line, for any given point, the distance to the line can be expressed in this way. See it? So I immediately substitute this one here, put this one to this one, okay? And you may ask, hey, you just mentioned it should be, for example, class 1 or class 2. Why don't you include the delta function here? For example, I is something like yi equals to 1 or yi equals to -1, right? Why you directly write yi here? Again, it's because of this. Because we assume that this line is in the middle. So I can do it for all the points. Who cares if you're class 1 or class 2? They must be the same, right? So in this case, I can simply write the inner level problem to be this. Okay, I take this W2 norm outside because W2 is not related with the choices of i's, so that I can model in this way. Now read this one again. I want to find a separating hyperplane such that this distance is maximized. That means what? That means outside of this level, you need to have another level which is a maximum problem. See it? You know what I mean? So this problem is actually what? A maximum mean problem. It's a bi-level optimization problem. Lucky there's no integers. No worry. I've seen some bi-level optimization problems with integers. It's gonna be the end of the world almost. Especially if it is nonlinear. Really, really difficult. Okay. Now the thing is, even if I don't have integer variables, this problem is still not that easy. And actually, this problem can be smartly formulated to a single level problem. And the form can be also simplified. To see how, let's have a look at the formulation. Where? So what I can do is that I can kind of rescale the W. For example, you can set, randomly give an alpha and set W equal to alpha W and the W0 equals to alpha W0. The purpose of this is to make this number to be 1, where our I star means the point, which is closest, I should say here, where I star are this kind of points, which is closest, the points that are closest to my separating hyperplane. Okay, so, and for other points, I don't care. What I care is that just for this kind of points, closest point, I'm gonna rescale such that their distance to the separating hyperplane is gonna be 1. Okay. So what is the point? The point is that suppose I have this constraint. That means, see, because I've already know the mean of this one equal to what? Equal to 1. See it? Why? Because my mean of this one equal the argument of I equal to 1 to n. What I mean is this part. The solution of this must be equal to what? Must be equal to 1, right? The solution of this must be equal to I star, right? Solution means which I will you choose? You're gonna choose I star, right? And the value, optimal value of this one must be 1, right? Because what? Because we have rescaled the W and the W0 such that at these points, the I star points, which are closest to this separating hyperplane, I have already this. Yeah. Come on. I already have this. So how about all other points, which are not this I star, just some regular points? For the regular points, I must have 1i times this is greater than or equal to 1. Why? Because see here, this distance is already 1. How about this distance? This distance is, of course, greater than or equals to 1, right? This is for the case of y equals to positive 1, okay? If y equals to negative 1, so you are going to have negative 1 times this. This is also negative, so it's still positive. See the point? So no matter in which class, at which point, you must have what? You must have yi times fxi greater than or equals to 0, which is here. Okay, this is the one in the parentheses. This is fx. Okay, clear? And now you see the point of hinge loss. It's really important. What is this? This is nothing but a hinge loss. And also have a look at my objective function. For the objective function, I think it's easier to see through this view, directly through this view. Let me clear it. Directly through this view. This is a very clear hinge loss. In other words, you want to maximize the minimum hinge loss. See it? So this is how we take advantage of hinge loss. No, I should say how we define the hinge loss for this kind of maximum margin classification problems. Okay, and the hinge loss is specifically emphasized or mentioned in SVM because SVM is a kind of like really a very, very representative kind of like tool for this kind of maximum margin classification techniques. And now we can actually have a what? Have a geometric interpretation of this reformulation. So after using these two things, then this problem, a bi-level optimization problem, is going to be equivalently formulated as this problem, problem 5, which is what? Which is single level, and it's a simple quadratic. Very, very simple quadratic. This is super simple. You can directly use first order method to solve, or later I'm going to introduce how to use the dual representation to greatly simplify it, further simplify it. Okay, and this model, in addition to this kind of algebraic explanation, you do have a geometric interpretation, which actually gives the name to support a vector. Why? Have a look at this. Again, we assume these 2 points are the closest point. And what is the difference? What is the distance between from here to here and from here to here? As what we just assumed, it should be equal to 1, right? However, if you just substitute, the equation inside, suppose consider the two equations, which is WTX plus delta plus W0 equals to 1, and WTX plus W0 equals to -1. Okay, consider this two. If you substitute, you're gonna see this one, the distance gonna be using that formula again. Using this formula again, because in this case, if y is +1, then this number is going to be +1, right? Because the equation here is equal to 1. If y is -1, then this number is going to be -1 because it's going to be -1. So we just substitute inside, then you're going to see the minimum distance going to be 1 over W2. And here is also going to be 1 over W2. So what is the distance between these two? We call it support vectors. It's going to be 2 over W. Well, every time it's going to automatically jump like this way. Come on, go back. Okay, so in this case, I can conclude that the distance between these two support vectors are 2 over the norm of W2. 2 over the norm of W, right? See it? 1 over norm of W plus 1 over norm of W, right? And now have a look at this one. You get a point what we are doing actually? What we are doing is that we want to try our best to split, to push these two support vectors as much as we can. See it? And that's the reason why we call it support vector machine. And why these vectors are called a support vector? Because please, every time it's going to jump automatically, because these points that lies exactly on these lines support our decision, support the margin. That's why they're called the support vectors. And the whole system, the whole technique is called support vector machine. Okay, so that is the geometric interpretation of this formulation. And later, when people mention this is actually called the hard margin support vector machine. When people mention the hard margin support vector machine, we all mean this formulation. Very few, in very, very few cases, people would mention this case, because I mean, what's the point to brutally solve this bi-level problem? It's very difficult. Instead, we're going to solve this one, which is much, much simpler. We're going to solve this one, which is much, much simpler. Okay. And just now I mentioned it's called hard margin support vector machine. The reason we call it hard margin is because we do not allow any misclassification. If you have a look at this constraint, you're going to see what? Any yi greater than or equals to, any yi equals to +1, I must have fx greater than or equals to 1. If y equals to -1, I must have fx less than or equals to -1. See it? In other words, there's no misclassification. That's why we call it hard margin. This margin is hard. This requirement is a hard requirement. We call it hard margin SVM, or you can call it fault-free. No fault will be tolerated, SVM. Okay. Now suppose I have already solved this problem. We say the solution is W star and W0 star. How would you make a prediction of a given data X? Simple. You just need to substitute this X into this F function. here we go. Oh, please come here. Okay, this f function. Okay, suppose you already have w star and w0 star. Then you're gonna see whether this fx is greater than or equal to 0, greater than 0. If it's greater than 0, then class 2. If it's less than 0, then class 1. What if it's exactly equal to 0? Forget about it. Here we don't discuss this case. In the soft margin SVM, we're gonna discuss this case. Okay. Any questions here? Mainly the motivation of SVM. The very, very basic motivation of SVM. Any questions? Again, this is the key. I want to find a separating hyperplane such that the distance between the two classes along the normal direction of this separating hyperplane will be maximized. Okay, this is the key. No question? Okay, let's continue. As I just mentioned, this is a what? This is a hard margin or tolerant or fault-free SVM. However, in many practical cases, you will never see this kind of ideal situations. You may probably see something like this way. Something like this, how to handle. Unfortunately, no matter how you try, it's impossible to find a separating hyperplane which is fault-free. No way. No matter how you choose the separating hyperplane, there are going to be some points with misclassification.
If we have a quadratic hyperplane, it's possible.
Yes, quadratic possible. But forget about this side. You are 2 steps ahead already. 2 steps. Step number 1 is a soft SVM, soft margin SVM. Step number 2 is a kernel technique. So here, let's pretend I don't have a quadratic. Okay, everything must be a hyperplane, which means everything must be linear. Okay, if it is a hyperplane, can you draw a line by any way? Draw a line such that you are gonna accurately classify, the two classes with on the training data. In other words, there's no misclassification. Can you do it? No way. You know what I mean? No matter how you draw the line. For example, let's try something for fun. For example, I try it this way. No, see, they're misclassified. I try it this way. No matter how I try, there will always be, something misclassified. See it? So in this case, how would you do? Is it a case that we're going to abandon the SVM? No way. And here's the idea of soft margin SVM, that we want to update the model such that some error means misclassification, can be tolerated. How to do it? Okay, now we're going to have a look at this graph. Again, I already rescaled my I already rescaled my W and the W0 such that I guarantee the distance here, for example, is 1. Okay, now let's see. Suppose I have 1, 2. Okay, let me circle this. Suppose what color shall I choose? For example, let's choose a purple color. Suppose I have 1, 2, 3, 4, 5. These 5 points you see, they're either misclassified or something weird. Okay, first of all, let's have a look at this point, and also this point. What I'm talking about is and also this point, as point 1, point 2, and a point 4. What are the common points of what are the similar? I cannot move it. Anyway, let me erase all of them and let me redraw it. Let's use purple color this time to do this. 1, 2, and 4. What are the common points? Or let's say why they are different from sigma 3 and a sigma 5?
Because they are in the wrong side of the hyperplane.
Very good. Yes. Sigma, let's call it this point 1, point 2, and point 4. They're in the wrong side. See it? They're blue color, so they're supposed to be class 2, which means they should be on this side of your separating hyperplane, but they are here. The same for X4, this node. It should be this side, but it is here. This means what? Misclassification, right? Okay, this is the first thing. The second thing, have a look at is class 3 and a class, sorry, have a look at the 0.3 and a 0.5. First of all, yes, they're inside, no problem. I mean, still they're, they satisfy the constraint. However, they satisfy the idea. However, there's a problem. They do not satisfy the constraint. Why? Because the constraint tells me that the distance of C of, let's say, call this point x3, of x3 to this point, to this separating hyperplane should be greater than or equals to 1. But clearly, the distance here, sorry, the distance here, yes, it's less than 1. Why? Because this distance is 1, and you are inside. This is called the margin region. You are, although you are in the correct side, but you are in the marginal region. So you are gonna violate this constraint. You are gonna violate this constraint. See it? Okay.
So I have a question here.
Yes. Yes.
Why we don't consider the support vector 2 as a vector that passes through x3? Because it's the, what is the reason?
Mm-hmm. Okay, I know what you mean. Yes. Here I just show you an example. This is possible, and in this specific case, yes, you can do this. You can, for example, make it smaller. But later I'm gonna show you that this is actually calculated by this model. By this model, it depends on the C, where C is a trade-off parameter. If your C is very small, then I would prefer, wait, let me see. C is very small, very big. Let me think about that. If your C is very, if your C is very big, it should not be very small. If your C is very big, then I'm not gonna, wait, give me 1 second. If your C is very small, yes. If C is very small, that means I can tolerate more such relaxations. That means I'm gonna put these margins relatively further, and I'm gonna tolerate the penalty of this. In other words, I would rather suffer this kind of relaxations. And if we go back to this example, the reason is that you can consider this later. For example, you just assume, okay, assume these W's and the W zeros are fixed. You know what I mean? Assume they are fixed. So far, you don't need to consider how to build this separating hyperplane and the support vectors. Suppose it's given. If that's the case, you know what I mean? You're gonna see these two types of violations. Type 1 is gonna be, not on the same side, which is a misclassification. Type 2 is the case that they're in the margin, right? Suppose they're given, okay? You agree with me?
Okay.
Okay. Now go back to your question. Why should I build the modeling, build the support vectors and the corresponding separating hyperplane this way? Why don't I, as we mentioned, for example, I move this part, this lines a bit closer, right? For example, somewhat like this way, right? So if that case, isn't it the case that, hey, I mean, it's gonna be, this situation is gonna be eliminated, right? What I mean is this. So let me use, what if I, for example, I draw a line something like this way? As Said mentioned. So in this case, yes, it's not, it's no longer gonna be an abnormal point. It's gonna be a very normal point. However, guys, don't forget that if you join this way, let me ask you, what is the distance here? You see, the distance of these two, the two new support vectors are what? Are smaller. That means what? The difference between the two classes is smaller. You see it? There is a trade-off that you want the two classes to be as different as possible, so that you have to tolerate this kind of problems, this kind of violations. Or you don't want to tolerate this kind of violations, but the cost is that the difference between two classes will be small. See it? So to this end, we actually use a parameter to reformulate it. Where it is, it's here. we can formulate the model, which is called SVM with soft margin, or you can call it fault-tolerant SVM in this way. So this part, let me draw a box. This part and this part is still exactly the same as the hard margin SVM, the same, right? The difference is that here first in the constraint, I added this one, minus CI for all the data. I is the ith data, okay? And this is actually what? A relaxation. That means, okay, for each data, I allow you to relax this very strong constraint. Be careful. Here, Kasi is only required to be non-zero. Sorry, to be non-negative. Kasi could be more than 1, okay? If Kasi is greater than 1, what do you see? This is going to be greater than a negative number. See it? And correspondingly, in this figure, what you're going to see? For example, these cases are Kasi is greater than 1. See it? This means what? Misclassification. The same here, 1, 2, 4. All of them, you can set Kasi greater than 1. And here, for Kasi 3 and Kasi 5, they are Kasi less than 1. What does it mean? That means I'm going to still keep the correct side. However, I'm going to enter the marginal region, which is inside, the region of the region between these two support vectors. Okay. So, however, Kasi must be greater than or equal to 0. Kasi cannot be negative, otherwise it's meaningless. Okay. And for clearly in this picture, again, suppose W and the W0 are given. Only these 5 Kasis are non-zero. Come on, go back. Every time it goes automatically. That really wastes time. Only these 5 Kasis are greater than or equal are greater than 0. All other Kasis must be 0. Why? Because, for example, consider this point. Yes, it is satisfied that 1i times fx equals to 1, greater than or equal to 1. It is satisfied, right? And for example, here, yes, 1i times fi is greater than or equal to 1, because here y is negative, equal to negative 1. Only points for these 5 points, it's not satisfied, and hence we need to add an extra or a slack variable, Kasi I, to make it satisfy and model it in this way. 1 minus Kasi I, okay? I should say we subtract a slack variable. On the other hand, in your objective function, you need to add this part. Why? Because think about this. If I don't have this part, I just have a problem in this way. What is your solution? Your solution would be what? Would be exactly the same as SVM. The SVM, the hard margin SVM. Why? Because who cares? I can just let Kasi to be relatively large. I don't care this kind of violations, right? I can, for example, even draw the 2 lines something like this way. I can draw the 2 lines, hyperplane something like this way. Who cares your misclassification? I just want to maximize this distance. Clearly not. As we just mentioned, we are facing a problem of trade-off. If my C's are big, then what's going to happen is that I do care the violations, this slack summation of these slack variables. In other words, I want this model to be, if possible, to be close to the hard margin SVM, so that I want the added slack variables to be small, right? And you can see, if my C's are small, that means it's closer to the to the hard margin SVM. If C's are large, that means I do care about these Kasis. I want to eliminate this kind of Kasis. Why? Because this is a minimization problem. Okay, Kasis are positive, non-negative numbers. So if C is a large number, then the second part will dominate this minimization problem. See the point? So by choosing different C's, by choosing different C, not C, different cost parameter C's, I can control the balance. Which one is more important? That's really kind of like a user defined. I cannot tell you what should you really select for this C. However, in many cases, people want to play, for example, c equals to 1, something like this way. Okay. Any questions about the motivation of this modeling, the soft margin SVM model? This is very, very important, the model itself. No? I think the hard model, the hard margin SVM is very easy to understand, right? The soft margin SVM is a little bit more difficult. The point is exactly here. After the class, please review the class notes and have a look at this figure. You're going to understand why we add this kasi and why this exactly shows the model here. Okay? Any questions? No? Okay. Then the following, yes.
I have a question.
Yes.
Can you show the picture?
Yes.
For those points that we have misclassification, the cassis should be less than 1 or bigger than 1.
Bigger than 1. What do you mean as this, and also
this,
right?
This one,
4.
Yep, cassis 4.
Yeah, 1, 4. It should be bigger than 1. Because if cassis is less than 1, that means what? That means 1 minus cassis is positive. 1 minus cassis is positive, that means what? You are in the correct side.
Oh, okay.
Right?
Yep.
The difference is that it's not greater than or equal to, what I mean is that the left side greater than or equal to 1. That means something like this kind of points. It's not only in the correct side, but also it must be out of the marginal region. It must be in this side of the support vector machine. Now, for example, this number, x3, because I have 1 minus cassis 3. Cassis 3 is less than 1. So that 1 minus cassis 3 is greater than 0, but less than 1, right? So what do you have? You have that this one, the yi times fxi is greater than 0. So that, yes, it's still going to be on the correct side. Okay?
Okay.
Yeah. Okay, very good. Any other questions? This is a very good question, by the way.
Yeah, I have one question.
Yes.
Suppose this cassis 1 is very close to red line, but it still is misclassified. But yes. It is from this figure, it's visible that distance is still less than 1. No. Be careful. Yi, you have a yi. This one is not only the distance. Okay, yeah, makes sense.
You have a yi, okay, and it's going to be negative actually.
Yeah. Okay.
Any other questions? No. Anyway, as a homework after this class, check this model, this picture together with the model model 6 very carefully. This is very, very important. Okay. It's 405. Let me see whether I should continue because it's going to take a long time. Okay, let me briefly introduce the dual representation here. I don't think I can finish, but let me briefly introduce it to save some time for the next class. So first of all, you can just simply solve it. Nowadays, the commercial solvers are very powerful. Solve this kind of problems. Even if you have, let's say, 1 million nodes, and let's say your dimensions are, let's say, the D equals to 100 to solve this problem, but it costs you less than 30, not to mention 30. I guess maybe cost you less than 20 minutes in this, in your, let's say, your laptop. I assume your laptop is a relatively new laptop, not something about 10 years ago, okay? And that's really powerful. However, it's still meaningful for us to have a look at some dual representations because the truth is that in many this kind of SVM solvers, they use the dual representation to even expedite the speed of directly solving this quadratic problem. First of all, we're going to use the Lagrange dual and the KKT again. So everybody knows what is the Lagrange dual, right? Be careful. You may ask you why you write in this way, because the Lagrange dual should be, come on, get out. The Lagrange dual should be in this way. Suppose I have a mean, let's say x, for example, it's called fx. Wait, I don't need to write down. I'm lazy. Easy way. Google. Lagrange dual problem. Dual function. Let's go to Wikipedia. Yes. Okay. Let me see whether it's something that I need. Ah, very good. Yeah. This is something that I need. Okay, so suppose the problem is minimization of this one. Okay, this is the problem. Can you see it? You can see it, right? Okay. Then the Lagrange dual function is formulated in. Holy, where's the Lagrange dual function? Okay, they formulate in this one. Okay, whatever they like. Just ignored. Here. Okay, so fx plus this lambda times f sigma of this, and then plus this nu. I don't know. This is nu, not v. Nu times h. Okay, but for the mu, for the lambdas, you do have a requirement that the lambdas are greater than or equal to 0. Arab, have you learned this one before? You've learned it, right? Because I know Said and Mahbouba, they must know it. Otherwise, that's serious. That's their research. Okay, so this is Lagrange dual. However, here you can see I use the minus. Where? I use the minus here. See it? I used this is this minus 1 minus Ci, right? What I'm talking about is this what I'm talking about is this box. Okay, this is from here, from this constraint. Okay, the reason I use a minus mu, did I use mu I? Actually use mu I, not mu. Yes, the reason I use minus mu I is because the constraint sign here is greater than or equal to 0. Okay, before that we've seen it is plus. The reason is because it is less than or equal to. See it? So they're the same. Okay. Then I after writing the Lagrange dual, what is this? Oh, this is LDA. Let me close it. After writing the Lagrange dual, what I can do is I'm gonna get a KKT condition, or for the stationarity points, you simply just get the gradient of the Lagrange dual, and then by partial L partial W equal to 0, W is a vector. Okay, I get this. Partial L partial W 0 equal to 0, I get this. The detailed calculation you can calculate by yourself. Partial L partial Ci equal to 0, then I have this. And then this is the what? The stationarity points, the stationary conditions of KKT. Arab, have you learned the KKT conditions?
Yeah.
You've learned, okay. So KKT conditions include, let's say, Mahbouba. Hey, Mahbouba, are you here?
Yes, I am here.
Okay. Let me ask you the question. Don't cheat, directly answer me. The KKT conditions include which parts of the conditions?
Which part?
Okay, let me ask you, KKT conditions are what? Under the name.
Okay, so KKT conditions are necessary conditions, but
Of
not
course,
sufficient.
Yes. And seriously, what I'm asking is something like PF, CS, DF, this kind of things. You know what I mean?
And these are first order conditions.
This is not what I'm asking for. Anyway, okay. To save some time, let me directly show the answer. So KKT conditions includes 4 groups of the conditions. Group number 1 is called stationarity, which means the gradient of the Lagrange dual with respect to the original variables, okay? Not with respect to the dual variables, okay? With respect to the original variables, the gradient must be 0 first. The second group of the KKT conditions is called primal feasibility, PF, which means if W0, Kasi, mu V, whatever, is a solution, then the primal constraint must be satisfied. And also you have Kasi greater than or equal to 0. This is a PF, primal feasibility. The third is called slackness, complementary slackness, CS. By the way, in linear programming, you also have the complementary slackness theorem. Okay, the complementary slackness tells you that the multiplication of the dual variables times the constraint itself must be 0. In other words, either the dual variable is 0 or your constraint is an equal constraint, a binding constraint, which means, for example, this one equal to this one, so that your mu I can be non-zero. And the fourth thing is what? The fourth thing is dual feasibility, which means that my mu I here is greater than or equal to 0. And my nu I is also greater than or equal to 0. Why? Because both of them are inequality constraints. Okay, they are not equal constraints. If they are equal constraints, then you don't have a limit about the signs. If they are this kind of constraint inequality, they are inequality constraints, then you must have the corresponding dual variables greater than or equal to 0. Okay, again, let me repeat. The KKT conditions are composed of 4 parts. They are primal feasibility. The first part should be the stationarity conditions. The second one is primal feasibility. The third is CS, complementary slackness, and the fourth one is dual feasibility. Clear? Corresponding to each of them. Okay, now what you can do is that you're gonna substitute the first 3 conditions into this dual function, and then you're gonna get a very, very beautiful form, equivalent form of this Lagrange dual. Some people call it a Wolf dual. It doesn't matter, you know. So the good point here is that in my original Lagrange dual, I have 1, 2, 3, 4, 5 decision variables. But here, everything can be represented by the dual variable mu. Okay, and this is super, super powerful, because if we do this case, immediately the problem gonna be converted to this way. And by the Slatter's condition, Mahbuba, explain what is Slatter's condition. Nonlinear case.
So in case of nonlinear, there should be a interior point.
For convex. Convex, not only nonlinear, convex.
Yeah, yes.
For convex programmings, Slatter's condition holds, means the strong duality theorem holds. That means solving the Lagrange dual problem is equivalent to solve the original problem. That Slatter condition means if there exists an interior feasible point. Interior feasible point means the constraint here is strict greater than, okay?
Yes.
And they're gonna be equivalent. So this is super, super powerful. Okay, anyway, due to the time limit, let me stop here. In the next class, I'm gonna introduce the dual representation here in a more detailed way, and also the kernel trick. The kernel trick is gonna be very interesting. That is, Said, probably you like it. That is something you mentioned that is quadratic, or even let's say Gaussian, which is even exponential function. Or we can use a neural network, neural network, the 10H. I don't know how to read it actually. I directly read it as tangent H function, and they're going to be something very, very interesting. Okay, that's everything about today's class. Where am I? Let me go back. I'm here. That's everything about today's class. Thank you very much, and you have a good day. See you next Monday. Bye-bye.
Thank you, sir. Bye.
Bye-bye.